Hello everyone, good evening to all of you. So again we came with a new video, and in this video we are going to discuss about the steady state temperature distribution again. So in our previous two videos we have discussed the steady state temperature distribution in Cartesian coordinate system, and in this case we will discuss the steady state temperature distribution in cylindrical coordinate system. Cylindrical polar coordinate system. Okay, so uh, one more thing I want to say as per your demand. Okay, from this video onwards, in this video also I will use two languages. One is Hindi and the second one is English. I will use English as a communication language for writing as well as for terminology in physics, and Hindi I will use to explain the concept. Okay, so let us start. तो चलिए सबसे पहले क्वेश्चन देखते हैं, क्वेश्चन में क्या है। आज का क्वेश्चन ये है कि कंसिडर ए सॉलिड सिलिंड्रिकल कूलिंग टावर ऑफ रेडियस 2 यूनिट्स वेयर एक्चुअली radius 2 units, so here radius 2 units and height 4 units. Okay, so its radius is 2 units, height is 4 units. Its base and the curved sides are held at 0 degree Celsius at the so base and the curved side are held at 0 degree Celsius and top at the constant temperature T0. Okay, so let us understand this first. So what happened? The top is maintained at a constant temperature, okay, T0. Okay, clear? So the top is maintained at a constant temperature T0, whereas the base as well as the curved sides are held at a 0 degree Celsius. Clear? Now the steady state temperature distribution is described by Laplace's equation del square T equal to 0. So this is given to us, the Laplace's equation, and we have to solve this one to find the steady state temperature distribution. Okay. So let us come to the question. What the question is: specify the boundary conditions. So in the first part, we are going to specify the boundary conditions. The second part, determine the steady state temperature distribution in the cooling tower. Okay. So let us start. So second one actually is to find the solution of the Laplace's equation. Okay. So how can you find the solution? Without the boundary conditions, we can't find the solution. Okay, particular solution we can't obtain. So in order to do that, we have to first specify the boundary conditions. So let us start with the point number 1. Boundary conditions. So boundary conditions means we have to find out what limitations that we have while solving the sum. Okay. So what it is, if you look into the question, the question says that the radius is 2 units, whereas the height is 4 units. Let us take the radius along x and y, okay, because radius has what circular symmetry. That means it is equal in all directions in the form of a circle. Okay, so we can say we can say that radius we instead of taking x and y coordinates here, we will consider rho as radius, and rho ranges from 0 to 2. Maximum value of rho is 2 and the minimum value is 0. Okay, rho as a radius. Let us take this one, rho as a radius. Then height. Height means here along z axis we have taken the height. So height is along z axis, so we can say z. Let us take it z. Okay, small z is equal to 4 units. This is equal to 2 units. Now it explains that the base and the curved sides are held at a 0 degree temperature. So curved side means what? What does the curved side mean? Curved side means where r is equal to, means rho is equal to, in this case rho is equal to 2, where rho is equal to 2 and z ranges from 0 to 4. Okay, z ranges from 0 to 4. At that point t is equal to 0. That means what you can say here. Okay, so when the radius is 2 units, okay, 2 units, temperature is 0 degree, 0 degree for Z ranging from 0 to 4. Okay, Z ranging from 0 to 4. This is given to us. Okay, so now mathematically, how can we write this one? Mathematically, we can write T2, and when Z is equal to 0 to 4 anything, so we can write Z T2Z is equal to T2Z is equal to 0. Okay, T2Z is equal to 0 for Z ranging from 0 to 4. This is equation number 1. The next one, when Z is equal to 0, Z is equal to 0 means near the base, along the base, because the base is maintained at 0 degree Celsius. So 0 degree, not Celsius, 0 degree. So the base is maintained at 0 degree. That means when Z is equal to 0, T is equal to 0 for any value of rho. Rho means radius, whether it is at the near the axis or along the curved surface. When Z is 0, T is 0. So what you can write here? When Z is equal to 0, okay, Z is equal to 0 means at the base for 0 rho 2, 0 less than rho less than 2. That means the radius ranging from 0 to 2, the temperature is maintained at a 0 degree. So mathematically, how can you write? Okay, mathematically T rho 0 is equal to 0. T rho 0 is equal to 0. Okay, clear? What about it? T rho 0 is equal to 0. So for what? For 0 less than rho less than 2. Okay, clear for that? That means for radius ranging from 0 to 2, when Z is equal to 0, temperature is 0. This is equation number 2. Now, when Z is equal to 4, means at the top, when Z is equal to 4 units, for 0 less than rho less than 2, means whatever the value of radius is, okay, the temperature is maintained at a T0. So mathematically what it is? T rho 4, when R is equal to rho and Z is equal to 4. At that point, what happens? The temperature is T0 for 0 less than rho less than 2. Equation number 3. Equation number 3. Okay. So these are the boundary conditions. Equation 1, 2, 3 are the boundary conditions. So we can write here equation 1, 2, and 3 are the required boundary conditions. Then what is next? The next is question number 2. We have to solve. Okay, to solve. So the given, so this one is cooling tower. Okay, so the given cooling tower given cooling tower has cylindrical symmetry. Cylindrical symmetry. Okay, clear about that? Cylindrical symmetry. Now what? Again, the steady state temperature distribution for the cooling tower is given by what? Del square T is equal to 0. Del square T is equal to 0. Okay. So this is the Laplace's equation. Okay. Laplace's equation. Now this Laplace's equation in cylindrical polar coordinates can be written as, now above equation can be written in cylindrical polar coordinates as how? Del square T by del rho square plus 1 by rho del T, sorry, del T by del rho plus del square Z by del Z square is equal to 0. Okay, so this is the Laplace's equation in cylindrical polar coordinates. Okay, let us take this one as equation number 4. Equation number 4. Now how can we solve this one? We can solve this one by using separation of a variable method. Okay, let us use the separation of the method of separation of variables. Okay, to solve above PD, partial differential equation. Okay, clear about that? Now T can be expressed as T rho Z is equal to R rho. R is the radius as a function of radius rho, and Z is a function of Z. Okay. Now differentiate. This is equation number 5. Differentiate equation number 5 with respect to rho and Z partially twice to get what? What to get? So let's see what we will get. Del T by del rho is equal to dr by d rho Z, and del square T by del rho square is equal to d square r by d rho square into Z. Again, del T by del Z is equal to r dz by dz and del square t by del z square is equal to r d square z by dz square. Okay, now let us take this as equation number 6. Okay, let us substitute the values of del square t by del rho square, del square t by del z square into equation number 4. Okay, equation number 4. What you will get here? Now, substituting the values of equation 6 into equation 4, we get, what do we get? Del square t by del rho square. What will have? D square r by d rho square z, okay, plus 1 by rho, and this one, that is dr by d rho into z plus this one, del square t by del z square plus r into d square z by d z square equal to 0. Now what we have to do? We have to eliminate this z from first term and z from the second term and r from the third term. How can you do that? By dividing the whole equation by rz. Now if you will divide the whole equation by rz, in the first term z and z will be cancelled, we will get 1 by r. And here also z and z will be cancelled, we will get 1 by r. Okay. And here we will get 1 by z. So what you will get? Divide the whole equation by rz, okay, to separate the variables, separate the functions, okay, the functions of independent variables, So how can you do that? By dividing it by rz. So what you will get? That implies 1 by r d square r by d rho square plus 1 by rho into 1 by r. Now d square dr by d rho plus 1 by z d square z by d z square equal to 0. Okay, now take this term containing z to the other side and keep the terms containing r on the left side. So by rearranging, what you will get? 1 by r d square r by d rho square plus 1 by rho into 1 by r into dr by d rho is equal to minus 1 by z d square z by d z square, okay, is equal to minus lambda square z. Now why minus lambda square? Why minus lambda square? Because we don't want this z to be periodic. That is the reason why we have taken minus lambda square. Then what we will get? That implies 1 by r d square r by d rho square plus 1 by rho into 1 by r. Now dr by d rho, okay, and this one minus lambda square equal to minus lambda square, and 1 by z d square z by d z square is equal to minus, this one minus, minus sign is there, minus lambda square. Let us now simplify the equations. Okay, so in order to simplify this equation, we multiply the whole equation by r lambda rho square r. Okay, so rho square r cancel, we will get rho square d square r by d rho square plus r cancel, one row cancel, we will get into rho dr by d rho, and here minus lambda square, and we have multiplied with the rho square r, so rho square r, and right side what you will get. So here how you obtain this one, multiplying by rho square r. Okay, we obtained by multiplying by rho square r. Here what you will obtain, minus minus cancel, z when will come this side, you will get d square z by d z square is equal to minus lambda square, sorry, not minus, lambda square z, minus minus cancel. Okay, so we will get a lambda square z. Now rearrange the terms to get what you will get, rho square d square r by d rho square plus rho dr by d rho plus lambda square rho square r is equal to 0, and d square z by dz square minus lambda square z is equal to 0. So these are the two required ordinary differential equations that we need to solve to find r and z. Then after that we can find t. And this equation, we take this equation as equation number 7. So this is equation number 7. This is equation number 8. Now equation number 7 is the Bessel function of a zeroth order. Okay, Bessel equation of a zeroth order. Okay, clear about that. So equation 7 represents Bessel equation of a zeroth order. Hence its a solution. Hence the solution is. So what the solution is? R as a function of rho is equal to what it is? J0. Sorry. It is C1 J0, and here we have lambda rho, okay, plus C2 Y0 lambda rho. Okay, Y0 is a function of lambda rho, J0 is a function of lambda rho, where J0 is equal to Bessel function of a first kind, and y0 is equal to, okay, Bessel function of a second kind. Okay, J0 means here we are representing J0 as a function of a lambda rho. Y0 means Y0 is a function of a lambda rho. They are the Bessel function of first kind and the second kind, respectively, of zeroth order equation. Okay, so we got this one. Let us take this equation as equation number 9. Now, what we have, we know that. So when so one thing, when the radius is very small, means almost to 0. In that case, what will happen? This y0 will actually tend to minus infinite. Okay, tend to minus infinite. So when we can write when rho is equal to 0 means along the axis y0 lambda rho, what happens? It diverges. Okay, when rho is equal to 0, okay, y0 lambda rho will will diverge. Okay, means what does it means? It means or it implies that when rho tends to 0, rho approaches 0, y0 lambda rho approaches minus infinite. Minus infinite. So when we calculate, so by replacing C2 is equal to 0 in equation number 9, okay. So by substituting C2 is equal to 0 in equation 9, we get, what we will get? We will get R rho is equal to C1 J0 lambda rho. Okay, let us take this one as equation number 10. Clear? So we got R rho is equal to C1 J0 lambda rho. Now we have one condition that when rho is equal to 2, rho is equal to 2. So in that case, what happens? For any value of z, okay, for any value of z, we know that it is um, what you can say 0. The value is 0 because along the curved surface. So this was the cylinder. Okay, so this is the axis. So when r is equal to means rho is equal to 2. That means we are talking about this curved surface. For any value of z is equal to 0 to 4. What happens? The temperature is 0. Okay, temperature is 0. So let us use the condition here. What it is that T. Okay, T. So we have, okay, we have T 2 and 2z. Any value of the principal z is it is equal to 0 for 0 z 4. Clear? That implies what? That implies R2 into ZZ is equal to 0. Now ZZ can't be 0. ZZ can't be 0. That implies what? R2 is equal to 0. R2 is equal to 0. That implies what? R2 means what? We have C1 J0, okay, lambda rho is equal to 0. That implies what? J0 lambda rho is equal to 0. Clear? So this is an equation, okay, which actually we have to solve. So if it will be solved, we will get the zeros of the Bessel function. So if R2 means this one is 2, huh? This is not rho, this is 2, this is 2, okay, this is 2. So J0 2 lambda is equal to 0. This we got. Clear? Next, if alpha 1, alpha 2, alpha 3, dot dot dot, alpha n be the roots of the Bessel function. Bessel फंक्शन, अगर बेसल फंक्शन के ये सारे रूट होते हैं तो मतलब क्या होगा? दैट मीन्स let us equate the nth root. Okay, so 2 lambda n is equal to alpha n. Okay, Bessel function, then equating the nth root we get, what we will get? Now 2 lambda n is equal to alpha n. That implies lambda n is equal to alpha n by 2, where alpha n is a root of or nth root of a Bessel function for n is equal to 1, 2, 3, dot, dot, dot. Okay, this is equation number 11. Equation number 11. Okay, so we got lambda n is equal to alpha n by 2. Then next, when z is equal to 0, in that case what happens? When z is equal to 0, for any value of rho, okay, in that case what happens? When z is equal to 0, for any value of rho, t is equal to 0. So when let us use that condition, when, okay, z is equal to 0, z is equal to 0, okay, t is equal to 0. That implies t is equal to 0 means we can write r rho and z0 is equal to 0. That implies, because r rho cannot be 0, that implies z0 is equal to 0. Now z0 means what? We know that z is equal to, okay, what the solution we have obtained? Z is equal to, till now we haven't actually found the solution. Okay, so we got this z0 is equal to 0. Now from equation number 8, okay, clear? This is equation number 12. Now using equation number 8, we have, what we have? The d square z by dz square minus lambda square z is equal to 0. We have, okay, this is a ordinary differential equation, second order ordinary differential equation. Therefore, the solution to above equation is what? Z as a function of z is equal to C3 cos h lambda z plus C4 sin h lambda z. Okay, so let us take z is equal to 0. When we will take z is equal to 0, okay, z is equal to 0, what we will get? Cos h 0, 1, sin h 0, 0. So this will become 0, we will get only C3. Z0 is equal to C3. Now, substituting this value into equation number 12, okay, substituting this value in equation number 12, we get, what we will get here? That C3 is equal to 0. Let us take this equation as 13th equation. Okay, now C3 equal to 0, replace this C3 equal to 0 in 13th equation, what you will get? So by substituting this value into equation 13, we get, what we will get? That z is equal to C4 sin h lambda z. C4 sin h lambda z. Okay, we got this one. So this is equation number 14. Okay, clear? So using equation number 14 and equation number 10 and 14. Okay, equation number 10, what equation number 10 tells? R rho is equal to C1 J0 lambda rho. Okay, C1 J0 lambda rho. And what is here? Z is equal to C4 sin H lambda Z. Okay, clear? So in generalized form, equation 10, equation 10 and equation 14. Equation 10 and equation 14 can be written as how it can be written in generalized form. So Rn as a function of rho can be written as C1n J0 lambda n rho Question is one. And Zn Z is equal to C4n sin H lambda n Z. Okay, clear? Therefore, the general solution is what? The Tn rho Z is equal to, so here n is equal to what? In every case, n is equal to 1, 2, 3, dot, dot, dot. Here also n is equal to 1, 2, 3, dot, dot, dot. Okay, so here we can write summation of n is equal to 1 to infinite. Okay, this into this Rn Zn. Okay, Rn Zn, Rn rho into Zn Z. So this will give us the summation of n is equal to 1 to infinite C1n into C4n then J0 lambda n rho into sin H lambda n Z. Okay, so finally we can write this. That implies Tn rho Z is equal to summation of n is equal to 1 to infinite an J0 lambda n rho sin H lambda n Z, where an is equal to C1n, C4n and lambda n is equal to alpha n by 2. Okay, so this is the required expression for the solution of the given equation and the steady state temperature distribution of the given function. Okay, clear about that? So this is all for today. Okay, I hope you enjoyed the lecture. Okay, clear? Now like, share and subscribe our channel. Okay, keep your bell icon on so that you will get notification whenever we will upload new videos. Thank you.